Okay, today how to detect serial correlation, in the regression model. So that we shall be checking today, how to detect serial correlation in the regression model. That we shall be checking today. Okay, suppose the model is something like this. And suppose we have all these variables. You can see from here: consumption, GDP, investment, right? We have three variables, and here the GDP is the dependent variable, right? That you can see from here. Just you see, this is our model, right? You can see our three variable. One is investment, GDP, and consumption. So that is our model, and so I make it big. That is our model. And here the data from 1970 until 1980. So meaning that there are 11 observation in total, 11 observation or 11 years data that we have here. Okay. Then okay, what we do, we can now we can okay, what we do, we open all the variables together, right? I open as a group, so you can see the variable consumption, GDP, and investment, that you can see from here. And here the GDP is the dependent variable, but consumption and investment are independent variable. So our model is like this. GDP is the dependent variable, right? And then C is the constant, right? Then consumption, right, plus investment. So this is my model, right? GDP is the dependent, consumption and investment are the independent variable. Now how to detect serial correlation in this model? Okay, so there are many ways. Suppose number one way is, we know that Durbin-Watson statistics. Durbin-Watson statistics, right? That is the one way to check the serial correlation, is one ways, right? Okay, to check serial correlation in the model. Okay, that is one way, right? Okay, and when the model is something like this, then we can apply Durbin-Watson statistics, right? When the model is something like this, right, then we can apply Durbin-Watson statistics. But if the model is something like this, GDP lag 1, right? I put a 1 variable lag 1, meaning that the dependent variable has become 1 period lag as a independent variable. Then for this model, Durbin-Watson statistics cannot be applied. For this model, Durbin-Watson statistics cannot be applied, or the Durbin-Watson statistics is not valid because the dependent variable has become 1 period lag. So when the model is something like this, right, when the model is like this, we call it auto regressive model. Then we must apply other test to check serial correlations. So the question is that then we can apply either Q statistics or LM test, right? So when the model is like this, auto regressive model, then we should apply Q statistics or LM statistics to check serial correlation. Okay, and now we shall apply it. And another problem, Durbin-Watson statistics actually for only one auto in the Durbin-Watson statistics you can use only 1 lag, not more than 1 lag, right? But here we can use a number of lag. In the Q statistics and LM statistics, we can use a number of lag. That means many lags we can apply. Okay, I proceed now. I estimate this model and see what happens. Okay, so how to estimate this model? What I do, I go to quick estimate equation. Okay, so here I write the model. GDP is the dependent variable, then C, then I put consumption, then I put investment, then I put GDP 1 period lag. So you can see the model, GDP is the dependent variable, right? Consumption, investment, and 1 period lag of GDP is here. So this model actually called auto-regressive model, and in this model Durbin-Watson statistics is not valid to check serial correlation. Okay, now we estimate this model. Right? Okay. So this is my result of the model, right? You can see. This is the result of my model. We can see from here, and GDP is the dependent, and these are all independent variable. Okay, but I want to check whether this model has serial correlation or not. That I want to check. I'm sorry, it has gone somewhere. Okay, it is the model. Okay, now the problem is that this model is auto-regressive model. So to check serial correlation, I shall apply either Q statistics or LM statistics. Okay, so I can do now. So that I can do now. So now so this is my model. Okay, now I go to view, I go to residual diagnostic, then first I check Q statistics as I told, right? I write the Q statistics as I told. Okay, here I take 10 lakh, right? Because here for the Q statistics I can take more lakhs. Okay, I take 10 lakhs, then I run the model. So this is the result, right, of the Q statistics, and this one is the autocorrelations, and this one is the partial autocorrelation, right? Autocorrelation and partial autocorrelation, and this is Q statistics and corresponding probability value, right? Okay, and for this model, so what is our null hypothesis? The null hypothesis is there is no serial correlation. That is the null hypothesis. So I am writing the hypothesis. The null is there is no serial correlations, right? That is null hypothesis, right? And what is alternative hypothesis? There is serial correlation, right? That is the alternative hypothesis. So what is, one is null and one is alternative. Okay, and you can see from here the probability is very high. All are more than 5%. You can see. So what about this one? 73.6%. What about this one? 86.7%. What about this one? 91.8%, right? So you can see all p-value is more than 5%. So we cannot reject null hypothesis. We accept null hypothesis, meaning that we accept this null hypothesis, meaning that in this model there is no serial correlations. This model is free from serial correlations. Okay. So that is the outcome of Q statistics. And what about LM statistics, right? We can check this one. That is, we call it actually Bush-Pagan LM statistics, that we can check now. So how to check? I go to view, residual diagnostic, then serial correlation LM test, right? I put it here. So first I try with lag 2, right? First I take lag 2, then I check. You see the Bush-Pagan serial correlation, and it is the observed R square and the probability, observed R square and corresponding probability. How much? 61.05%. 61.05%, which is more than 5%. So we cannot reject null hypothesis, meaning that it is our null hypothesis, no serial correlation. That means this model does not have any serial correlations. Okay, and in this model, in this Bush-Pagan LM test, we choose 2 lags, right? It is here. You can see the 2 lags. So according to the this test, the dependent variable is the residual, right? You can see residual, and you can see from here there are 2 lag 1, lag 2. You can see from here, right? 2 lags are the independent variable and receipt is the dependent variable. Okay, so but here I have chosen 2 lags, so there is no serial correlations. But what happens if I choose 4 lags? So I go to view, residual diagnostic, serial correlation, LM test. Okay, last time I took 2, now I take 4. Then I check what happens. Okay, 4. Okay, when I take the 4, observed R square and corresponding p value, right, is 31.94%, meaning that I cannot reject null hypothesis. Rather, I accept null hypothesis, meaning that there is no serial correlation in the model. You can see from here this test, the Bush-Pagan test. Here the dependent variable is receipt, and we have 4 lags. You can see from here, right? Receipt 1, receipt 2, receipt 3, receipt 4. So what is our now decision? Our decision is Q statistics is telling, according to the Q statistics, there is no serial correlation, and also according to the Bruch-Pagan test, there is also no serial correlation in the model. Because so, the model is free from serial correlation. So, we can use this model, for hypothesis testing or forecasting. Because this model has no serial correlation, so we can use this model for forecasting or hypothesis testing. Normally, when the model is free from heteroscedasticity, when the model is free from serial correlations and so on, then only we can do hypothesis testing or forecasting. But if the model has so many problems, such as if the model has serial correlations, or if the model has heteroscedasticity, or in that case we cannot test for hypothesis, or we cannot use the model for forecasting. So meaning that the model should follow all the assumptions of regression line. In other words, if the model has no defect, if the model does not have any defect, only then we can test the hypothesis or we can go for forecasting. So that is the guideline all the time. I'm writing here, you can see, I'm sorry, if an estimated regression line fulfills all the requirement of a good regression model, only then we can go for hypothesis testing or forecasting, such as forecasting. Only then we can go for hypothesis testing or forecasting. Suppose a model and estimated regression line has no heteroscedasticity or no serial correlations, etc., etc., then we can go for forecasting or testing the hypothesis. So I am saying again, if an estimated regression line fulfills all the requirements of a good regression model, only then we can go for hypothesis testing or forecasting. Suppose an estimated regression line has no heteroscedasticity or no serial correlation, etc., etc., then only we can go for forecasting or testing the hypothesis, not before that. So meaning that we have to make the model correct first, right? We have to make the model perfect first. Then only we can go for forecasting. Not before that, right? So that is the guideline. Okay, suppose we check for this particular model. Okay, so we have done it now. We have done it now. So now I proceed. Thank you very much for being with me.